Hello everyone, and welcome to the third question of this. My name is Carlos, and I am the current president of Oxford University Scientific Society. As you probably noticed, we are running the events of weeks 1 and 2 online to avoid COVID-19 and freshers flu, and also to give a chance to everyone in Oxford and elsewhere to listen to our speakers. Just as a quick reminder, we are going to resume in-person events in November, starting in November 4 with a talk by Professor Gero Miesenberg. Details of the venue will follow soon, so please follow us on social media. Today, we have the privilege to host Dr. Chiara Marletto, a research fellow at the Department of Physics and Wolfson College here in Oxford. Chiara is a theoretical physicist, and she specializes in the theory of quantum information, most commonly known to be the foundation of quantum computing. Some of Chiara's recent research, working together with another Oxford quantum pioneer, Professor David Deutsch, has recently proposed a generalization of the quantum information theory that is known as constructor theory. With this theory, it is now possible to address multiple issues at the foundation of the theory of control and causation in physics, and I suspect she's going to tell us everything about it in the talk today. If you have any questions for Chiara, please feel free to ask them in the comments below, and we will read them out for you at the end of the talk. Thank you very much for joining us, Chiara, and I will now hand over to you.
Great. Thank you very much for inviting me. So I'm very happy to be speaking at this event. So as I think Carlos said, my talk will be a description of a new approach that I've been working on for a while in Oxford here with David and other colleagues from the physics department and beyond that, which is trying to develop tools to go beyond what currently is known as quantum computation. So it will kind of start with some considerations about quantum computing, and then it will move on to discussing what this new approach is about. So to start with, you might have heard in the news recently this kind of great buzz about quantum technologies. So I think the quantum computing enterprise started as a theoretical attempt to kind of expand on the scheme that Turing provided us with for a programmable computer, to include quantum effects in this computational scheme that Turing invented. And then it moved on to become actually a huge kind of technological and engineering enterprise that cuts across different university departments around the world, as well as research units in big companies. And so aside from these huge titles about quantum supremacy that would show how quantum computers actually are better than any classical computing machine, there's also this quantum computing race that is actually taking place now, where different tech giants around the world are trying actually to develop the first convincing array of working qubits that can demonstrate this theoretically predicted quantum supremacy of the quantum computer. And of course, there are different bets on different technologies. And so from the engineering point of view, this is really exciting. But so I'm going to move away from the headlines for a bit, because what I'm interested in is actually nothing to do with this. So this is a very interesting thing that's going on, but I think that's not the focus of my research, and it's not the focus of this talk, because this talk is trying to go beyond this. So in a way, quantum computation has become now almost like as I said, it's a part of the engineering and technology type of kind of set of problems. But I'm a theoretical physicist, and what I'm interested in is to understand whether we can improve on the foundations of this enterprise to make it even better in some sense. And so the question is, how can we make it better? Because it looks like when you talk about universal quantum computers, that's all there is to hope for. And actually, it's not true. And that's kind of exciting, I think. And this is where actually my journey in this research started, because that's one of the things that I first learned from David when I was doing my PhD here in Oxford. So the idea is that actually quantum computation, the theory of quantum information, is really an unfinished revolution. So on the one hand, it's a revolution because it taught us that the study of devices that are pertain to the human domain, if you like. So they are man-made objects that power our technology, can actually illuminate the foundations of physics. And this is a very counterintuitive thing. It was revolutionary at the time when it was proposed in the 80s, and it took quite a while for the community to actually absorb this fact. The fact that by studying the fundamental laws that put limit on computing machines that can run on the laws of quantum theory, we can actually understand quantum theory better. This is quite cool. But it's an unfinished revolution because when you open a quantum computation textbook, for example, or some kind of paper that's written about the topic, you will see that aside from the technical details, all the proofs, all the things that have been demonstrated fully rely on the laws, the dynamical laws of quantum theory, which is, as we know, one of the kind of two best explanations that we have at the moment, the other one being general relativity. But as such, we expect it to change in the future. And one of the issues with quantum theory itself is the fact that it doesn't agree with the description of physical reality that general relativity provides, because general relativity is fundamentally a classical theory that doesn't have quantum effects. And so there is an expectation in the theory community in physics that this quantum theory itself will have to be modified in one way or another. And so the idea is, can we still retain all of the results from the quantum theory of computation about universal quantum computers without having to rely so much on a theory that may or may not be changed in the future? So that's kind of the first reason why we might want to go beyond quantum theory, the quantum theory of computation itself. The second reason, which is the reason actually why I ended up being interested in this thing that I will later tell you about, which is constructor theory, is that there is another reason why, there's another reason why actually it's not proper to say that a universal computer is the most universal programmable machine that we can think of. In fact, it's not. And so if you think of the definition of kind of universal computer, very broad general terms, is that it's a computer that can be programmed to perform all physically possible computations. But there are transformations in the physical universe that are not computations, and they are not in the repertoire of the universal computer. And one of them, one of these interesting tasks is key to the phenomena of life. And this transformation is self-reproduction. So self-reproduction is a transformation that cells undergo in kind of biology all the time. And it's quite funny that a universal computer actually can't perform it. It can't perform it because if you think of programming your kind of computer to produce a replica of itself, we know this is not possible. And this is not possible not because the computer is somehow ill-built or kind of lacks some memory or some speed. It really does not pertain to the general theoretical model that Turing thought for a programmable universal computer. And whether it's quantum or classical, that doesn't make a difference. Now, this was pointed out by von Neumann. So von Neumann noticed this fact, and he gave a number of beautiful lectures on the topic of how to emulate life with artificial programmable machines. And that's how he realized back in the 50s that a universal computer is not the most universal machine. So then he invented a more universal machine that he called the Universal Constructor. So this is a programmable machine that can perform any physical task that is permitted under given dynamical laws, under given laws of physics. So you can think of it as like a kind of universal, all-powerful 3D printer, which can also, among other things, if it's possible, can also create a replica of itself. So it can be programmed to create a copy of itself, unlike the universal computer. And so the natural question for a theoretician is, how can one generalize the theory of quantum computation that we currently have to cover these kind of machines, not just ultimately, yes, the universal constructor, but even just programmable constructors? How can we generalize the theory that we have at the moment for universal programmable computers to include these other types of machines that are important, and they are actually key, if you like, to the next technological development that we could think of, probably in a very long time from now. But it's kind of something that we could think ahead about. So these are the two reasons why I think we want to go beyond the quantum theory of computation. And in this presentation, I will just talk you through a number of things that we can do in order to realize these two to address these two problems. So to do this, I will ask you to kind of follow me down a sort of rabbit hole, if you like. So we need to look at, to give a broad look at actually how physics formulates its laws. And then we can try to address the two problems by considering a kind of radical step forward. So first, let's take a look around and consider the guesses that we've had about the universe so far. So actually, there are not many. Well, probably we probably made lots of guesses, but I think those that were successful and worked as good explanations for what's going on in the universe are really few. So there's like Newton's laws and Maxwell's equations, which compose they are the first important development of modern physics, and they describe respectively the kind of dynamics of gravitation and masses, and the physics of light, in the case of Maxwell's equations. And then there's, of course, the theories that superseded those two. One is general relativity, the other one is quantum theory. And I just wanted to label the first three in this list as completely classical theories. So these are theories that do not have quantum effects. So they are sharply different as far as their measurement theory and as far as the information theory that they can sustain from quantum theory itself. Now, although they kind of look, all of them, they look very different from each other, but there is one thing that they all have in common. And this thing is that they use dynamical laws to describe trajectories of objects in space and time, given some kind of initial condition. So if you think about it, the mode of explanation that Maxwell's equations, general relativity, and quantum theory all implement hasn't really changed much since the mode of since Newton's time. So we've been using this mode of explanation that uses descriptions about what's happening given some initial conditions. And somehow the idea is that this is all there is, and this is all we can do to explain in the most fundamental way within physics the physical reality around us. Now, I'd like to kind of offer a challenge to this view. And so I'm going to claim that there are actually phenomena in the physical world that are not explainable exactly in terms of laws of motion and initial conditions. And this is like a fact that I think has been known for a while, but somehow it should be stated in a stronger way. So that's what I'm going to do now. So I'm going to give you a few examples of these phenomena. So if you consider, for example, the physics of information, it's very hard to express the concept of a bit. Let's just talk about the classical bit for the time being, in terms of dynamical laws and initial conditions alone, because the fact that a bit is a bit doesn't quite depend on the state it is in, given a given sort of initial condition for the system in question. But it depends on the fact that it is possible to perform a number of transformations on it. So, for example, it's possible to change 0 into 1 and 1 into 0. And also, it's possible to copy these two states onto another bit if a second bit is available. So this is a property of about what can or cannot do or cannot be done with the bit, rather than about what happens to it once it's on a given fixed trajectory, as a certain dynamical law prescribes. And similarly, there are other properties of objects that are also about possible and impossible transformations. And here are listed thermodynamic properties of heat engines and possible and impossible machines that thermodynamics studies. So again, these what qualifies something as work or heat is to do with what kinds of transformations are allowed on kind of the physical system in question, rather than what particular state it is in. And then you can go even further. And of course, there is a whole phenomena of the physics of life. So if you consider the explanations for why, how there are kind of living systems in our universe, the explanation could be given, of course, in terms of, well, there was some initial condition for the universe at some point, and this was evolved through a dynamical law, and that meant that at some point, kind of an elephant popped up on Earth. So that's one way of explaining that. But it's not the explanation that we want, is it? In fact, the explanation that we want for an elephant or a giraffe or whatever else we are wondering about is the explanation that Darwin's theory of evolution gave us, which is the fact that it's possible that such an entity with a given complexity can come about from very simple beginnings where there are no such complex entities around. So this explanation is all about explaining that something is possible, starting from kind of some allowed natural occurring materials, rather than giving like a dynamical law that evolves elementary constituents of the matter one time after another, given a sort of initial condition, because that wouldn't be a good explanation for life, really. So these are two broad categories of objects that we know are compatible with dynamical laws, and the fact that they are composed of atoms is a good fact that we know, and we know that the atoms obey the ultimately dynamical laws that we currently know, but can't be explained in terms of those dynamical laws. So as I try to convey now, the one thing that all of these phenomena have in common is that their essence, the key to explaining them, is not about what happens to them, so what you can call the actual, but about what transformations could or could not be made to happen, which I like to call the counterfactual. And so I can give you like a better example, maybe to just make these terms a bit more familiar. Can think of chess and trying to describe, to provide a number of properties for this knight and this lone knight on the chessboard. One is to say it's in a specific cell, for example, E4. That's a kind of actual property of the knight. But then there are other properties that are counterfactual, and they have to do with what transformations can be performed on it or cannot be performed. And so the fact that it can jump to any of these red squares is a counterfactual property of the knight. And to continue the analogy and the example, there are some facts that can only be explained actually in terms of counterfactual properties of a chess piece. So, for example, one could ask, given a configuration of this sort, why is it that it's impossible to achieve a checkmate? Now, the impossibility of this could, of course, be explained if you talk about a specific game that's actually happening with two players. You could, again, explain it in terms of, try to explain it in terms of giving the initial conditions of the universe and then working out what that means for what the two players will play after they've reached this particular configuration. But that's not explaining, it's kind of missing the point, because the point that we want to explain is the impossibility of reaching one particular further configuration, which is checkmate. And this is really due just to the counterfactual properties of these pieces, where they can move and also where they are now. So the best explanation about this fact is counterfactual. Okay, so what do we do with this? So can we actually turn these considerations into something useful? So we just said that there's a whole bunch of phenomena that we know about, which we would like to explain within physics. We know are compatible with dynamical laws as we know them, but they're not completely explained by these laws. So should we give up on these phenomena, or can we somehow find a way of incorporating them into physics? And also, will this bring us back to our original problem, which was how to extend the quantum theory of computation beyond what's its current domain? And surprisingly, actually, we can do all of that. And so to do that, we need to look at another host of laws of physics that we already have. So earlier I cheated a bit when I said that the only physical laws that we've had good guesses about the universe so far are the dynamical laws that I mentioned, because there are some pretty good guesses, which actually turn out to be all about counterfactuals. So we are actually already using counterfactuals in physics quite a lot. So that's kind of a good thing. So here are a few examples. So you've got the energy conservation, which is a law that says that a perpetual motion machine is impossible. So again, it's a law that constrains dynamical laws, so it's more general than any of them, and it's about impossibilities. Likewise, if you like, you can think of the second law of thermodynamics. There are different versions of it, different formulations, but one thing they have in common is that they rule out some machines. So they say that some machines are impossible, specifically, if you want to formulate this way, that a machine that can convert all heat into useful work with no other side effect. And finally, even the kind of core principle of quantum theory, which is Heisenberg's uncertainty principle, which is usually popularized as saying that if you look at an electron, quantum particle, you cannot observe with arbitrarily high accuracy jointly its velocity and its position, is about ruling out the possibility of some machines, which would be these machines that can actually measure these properties perfectly at the same time, which is what we get in classical physics, where the Heisenberg's uncertainty principle is violated. Another way of looking at it is to say that it's impossible to copy reliably all the states of a quantum system or of a qubit. So again, this is about the impossibility of a machine. So we see that there are all these principles that we're already using, and they are appealing to possible and impossible transformations, so counterfactual aspects of physical systems. So the natural question is it possible to use this can and can't approach, generalize it, make it even more powerful, and try to use it to explain the phenomena that I was mentioning earlier, and then perhaps also explain dynamical laws themselves? So it's kind of a very ambitious question, and I think this is what leads us directly to constructed theories program, which is, in a nutshell, is the idea that fundamental laws can be expressed as principles about what transformations are possible, what are impossible, and why. And this is what kind of should explain at the most fundamental level everything that we have in a universe. And then dynamical laws can actually be considered as emergent consequences of these deeper principles, and can be explained in terms of them. And so can the initial conditions. And I think so. This constructed theory program was kind of proposed by David Deutsch around about, let's say, 2011, which is exactly when I was doing my PhD. And then since then, we started collaborating on it and trying to apply this approach to a number of problems in fundamental physics. And so it turned out that there are actually two ways of looking at constructed theory. So on the one hand, we can look at it as a way to expand on the theory of computation or quantum computation in the way that it emancipates it from quantum theory itself on the one hand, and also it can help us deliver the theory of the universal constructor. So it somehow plays the role of addressing the initial problems that I mentioned. But at the same time, it's also a proposal for new physical principles that underlie phenomena of information theory, thermodynamics, and also the physics of life. And the hope is that it can somehow deliver this visionary project that, in a way, von Neumann already envisaged, that you could unify quantum and classical information, thermodynamics, and the physics of life all in one theory, which would also help us understand better the foundations of physics themselves, just like quantum computation has helped us understand better the foundations of quantum theory itself. Okay, so here is the program, and now I want to transition to kind of the second and final part of the talk, which is great. So we have all of these nice desiderata, and we are hoping to be able to deliver this kind of vision. But in the meantime, so these new counterfactual laws that we have already conjectured, are they useful? Can they help us understand better phenomena that we are aware of? Is there anything that we can apply them to? And so, so I want to tell you a bit about one of the ways in which we can apply these principles. And to do that, we need to take a little detour. So I will need to kind of follow me into sort of collecting a few ingredients to understand the problem that I want to tell you about, which you can think of, let's say, the first application of this more general approach to delivering some kind of experimental scheme. Okay, so the first ingredient is what we call quantum entanglement. So entanglement is one of the key features of quantum theory, and you don't need to know much about it for the to kind of follow the rest of the talk. The only thing that's important to know is that it's a form of correlation, so it's something that you can establish between at least kind of two subsystems, And just like correlations is a property that can be established through interaction. And so the other feature is that it's a kind of correlation that only quantum systems can have. So if you can verify that two systems, two photons, for example, are entangled by making suitable measurements on them and checking their correlations in a particular way, then you can conclude that they are behaving in a kind of, they are displaying the full potential of quantum theory. And this is why entanglement is actually key for phenomena like quantum computing on the one hand, and then quantum cryptography and so on. But the key thing is that it's a correlation, and you need to perform some measurements on the particles involved in the phenomenon to verify that they are entangled. Just like when I tell you there is a correlation between my socks, you would have to look at their colors to verify that that's the case. So the second ingredient is a problem that I already mentioned at the start of the talk. And this is a problem with the way we describe gravity. Roughly speaking, there is an embarrassing problem at the foundations of theoretical physics, which is that on the one hand, general relativity is the current best way that we have to explain how gravity works. And it's about a century old. And the problem is that it says that gravity isn't quantum. So it's a completely classical theory. And given that both general relativity and quantum theory are hoping to be universal in the sense that they apply to everything in the universe, there has to be a clash. Something has to give. Either general relativity has to change, or quantum theory has to change, or both have to. And the reason why that is that there is a key issue that arises when you think of this problem. There are objects with a mass, so objects that respond to gravity, that can also be in quantum states. So they obey Schrodinger's equation, and they can kind of display quantum effects. Specifically, they can be put in a superposition, in a quantum superposition of two locations. And once you are in this state with this massive object, the question is, what happens to gravity? So if gravity is classical, there's no hope that it will interact quantum mechanically with this other object. So the idea is that the quantum mass would have to become classical some way if it is to interact with gravity, and if we think the gravity has to be classical. Or the alternative is to think, well, now maybe ultimately actually gravity is not classical, it obeys quantum theory, and so we have to modify Einstein's general relativity to make it into a quantum theory. And so this is the first answer that I listed here, and it's what powers the kind of several proposed approaches to the field of quantum gravity. So these are all proposed dynamical laws to describe a kind of quantum system that has a mass or an energy that interacts with the gravitational field in such a way that the gravitational field becomes quantum. Now, the problem is that none of these theoretical proposals for quantum gravity are actually making predictions that are within experimental reach. So they are nicely developed from the mathematical point of view and conceptual point of view to some degree, but they are not verifiable experimentally. So kind of Feynman already suggested a way to resolve this problem of does gravity behave in a quantum way or not with an experimental test. So, you could kind of put mass into a quantum superposition, then see whether the gravitational field responds in a quantum way, and perform some kind of test to see whether really gravity is quantum or classical. But the problem is that, as I said, the predictions from quantum gravity are not actually easily testable, because gravity is, let's say, kind of informally speaking, is a very, very weak phenomenon. So it's very hard to detect any quantum effects in it. But is it just because of that, or is it because we don't have the right set of tools to try to think of an experimental test? And the answer is that there are ways of making predictions in this domain where, say, dynamical laws that we know are difficult to apply because we really don't know which dynamical law can apply in this context, given that the ones we have are saying contradictory things. And these tools that we can appeal to are these counterfactual principles I mentioned earlier. So that's kind of the exciting thing that I'm kind of building towards with this talk. And this is the application I want to tell you about. So what happened is that you can show that by using this general constructor theory's counterfactual principles about information, you can show that there is a way to check whether gravity has some quantum features. And this is expressed by this simple line here, which says that if you can do an experiment where you show that gravity can create entanglement between two masses, then gravity must be quantum. So the experiment would have to create the right conditions for two masses to become entangled, so especially correlated in the way that I said earlier, through the channel of gravity, not through other forces or interactions, and then verify that the masses are entangled. And if you could perform this experiment, you can safely say that whatever is doing this mediation, in this case gravity, has got to be non-classical. So it can be described by classical theory, which would then somehow confirm the idea that quantum gravity is the correct way of looking at gravity, so solve Feynman's problem. And this generated a lot of excitement. So I think this is some work I've done with Vlatko Vedro, and it's also underlying a test which was proposed kind of in parallel by a team in London led by Sugato Bose. And so this was very exciting because I think after many years of kind of trying to come up with experimental tests of quantum effects in gravity, finally that looked like there is a way of actually achieving this, at least in this in-principle manner that I just described. And the upshot here is that if you were to successfully detect entanglement between the two masses in the lab, then you would be able to actually refute in one go, using this result that I mentioned, all classical theories of gravity that conform to the principles that I was describing, including Einstein's general relativity. So this would be a complete, in a way, confirmation of the idea that we have to press on this program for quantizing gravity, rather than thinking that Einstein's general relativity is sufficient to describe gravity itself. And so you might be asking, how far are we from delivering this goal? And this is the aspect that actually made experimentalists, I would say, slightly optimistic. So to explain this, I sort of showed you, I want to show you like the way in which experimentalists would try to judge a proposal of this kind. So the first thing that they would be asking is, how massive are these masses that we have to manipulate quantum mechanically and get entangled through gravity? Because there are some technological limitations right now, insofar as about the masses, how massive an object we can put into a quantum superposition. And the answer is that we are actually not that far from what we can do right now with this proposal. Because if you look at this line, so right here on the left, there are electrons that I haven't put on this diagram. Then here we have like masses that are a bit larger, so 10 to minus 24 kilograms, famous buckyballs. if you're interested in this kind of stuff, you can look for the experiments where buckyballs were made to interfere, just like photons. It's just the photons are massless and buckyballs are quite massive. So that was already an incredible feat that was achieved. And then here we got viruses. So they are kind of about this mass, so 10 to minus 17 kilograms. And roundabout here is the current technological limitation for objects that we can put in quantum superpositions. And the masses that we will need for this experiment are a bit larger, but not that larger. So it's 10 to minus 12 kilograms, about the mass of a human cell. And then, of course, on this side, we've got Schrödinger's cat, which is far, far, far more massive. We're nowhere near yet close to kind of performing that nice experiment that Schrödinger thought about, where the cat would behave quantum mechanically. But we're kind of moving slowly along this line, and my guess is that at some point we will get there. But in order to perform the experiment I mentioned, we need to create a quantum state of an object that is about this size. And this is challenging experimentally, but I think it's somehow within reach, much more than kind of the hopes that you would have had just by looking at some of the kind of quantum gravity predictions for detecting quantum effects in gravity. And so this is very exciting. And that's the kind of ending point of my talk in a way. So this is like an example of a first application of these principles that are that describe computations and tasks that go beyond, let's say, quantum computing itself. And they go beyond also dynamical laws, because they can apply in domains such as the one I just mentioned, where we are not sure which dynamical law we should appeal to, or let's say the dynamical laws are intractable and it can be applied for the say practical reasons. Whether or not this is going to be performed, this experiment is actually something that we'll have to see in the future. But I think there's currently a lot of interest, and I'm really hoping that it will be possible to perform it so that we can kind of maybe perform one step forward towards understanding how gravity behaves in a kind of quantum way. And my guess is that these principles will be a key to construct the future theory that will kind of supersede both quantum theory and general relativity. So I'll kind of thank my collaborators, and I think I'll stop there, and thank you for listening. I'm very happy to answer your questions. Thank you very much.
Oops. Yes. Wonderful. Thank you so much for that talk, Kiara. I have personally learned a lot, and I'm sure many of the members of our audience will also have learned very much about physics in general and your work in particular. We are now going to have a brief Q&A. So I'm just going to start with a question for myself while the audience starts writing up their questions.
Yes.
So you've mentioned that one of your objectives is to apply constructor theory to things like biology as well, apart from the sort of litmus test that's going to be the gravity experiment.
Yes.
So how are you planning to do something like that?
So I think the part of the talk where I described this was mostly outlining a vision. So in a way, it's something that I may not do directly myself, but I'm hoping that constructor theory will provide the tools to be kind of applied to biology. And the way I see this is that it seems to me biology has made great progress in understanding the basics of life, how it works, and so we have a very nice descriptive understanding of kind of some of the basic mechanisms for living entities. But somehow what I'm interested in was to deliver this program of von Neumann. So trying to understand, rather than describing what biological system we already have and we happen to have on Earth, I'd like to understand what are the fundamental limitations for a living being or a living system, intended more broadly than just those that are naturally occurring, but even including things like artificially created entities. And so in that sense, I think there's a lot of work to do there. And perhaps it also includes, broadly speaking, the task of fully emulating, let's say, what a thinking human being can do. So these are two open problems, I would say. One, understanding what are the physical limitations for the phenomenon of life. And second, to understand what it means actually to fully emulate what we currently describe in an informal way as thinking. And my view is that although there are lots of kind of nice proposals for doing that, but somehow we haven't quite got physics into the game in a powerful way yet. And I would like to see that happen. And my guess is that this approach of constructor theory can provide methodologies to do that. Maybe it's not something I will do, but I think I'm hoping that there will be some, smart theoretical biologists out there, and maybe some other physicists and computer scientists who will get together and use these tools to approach these two problems.
And well, of course, you're just the pioneer of this, and hopefully this will become an entire branch of work where people can do their own contribution.
Yeah.
So our next question is from the audience. Well, this is a little bit of a funny one. How much time until this question is solved? And I guess this question means the gravity experiment that you mentioned.
It's unpredictable, I think. So I think this is... so, as I said, it's been quite a long time that we've been trying to resolve this issue. If you talk to the physics community, there is a large part of the community that is already working on quantum gravity, and they have nice theories proposed. And so for them, it's just more like they're thinking it's like just a matter of waiting for the experimental confirmation to come along. There are parts of the physics community that are more skeptical about it. And what I'm hoping is that this experiment, which is somehow enough within reach to be realized, by kind of the current technological tools that we have, is that this. So I'm hoping that this experiment will at least just focus everyone on the kind of search for the right theory of quantum gravity, rather than having still this debate about, is gravity quantum or is it classical? So I'm really hoping that this is a kind of good step forward. When it will happen, I have no idea. I think this really depends. It's a bit like asking when will we have a fully fledged universal quantum computer. It's really hard to predict. So I mean, watch this space, I would say.
Brilliant. Okay, I think we have time for perhaps another one or two questions. Lorenzo, can you show the next question, please?
Yeah. So this requires a little bit of explanation, because I had the opportunity to have a look through your book. And I think in either the introduction, chapter 1, you mentioned this example of a lifeboat in a ship. And you say that basically it's there because shipwreck can happen. And so this is the counterfactual explanation for that. And I was actually, because in the past I had the opportunity to actually study quite a lot of philosophy. In my philosophy classes, pretty much the important thing was about the scientific revolution, at least. Let's say the big topic was that the big introduction of science at that point was that final explanations, so final causes, were sort of discarded as wrong explanations, and only basically efficient causes were kept. And so just to clarify this doubt of mine, what makes a counterfactual explanation different from a final explanation? For example, in this case.
I guess it depends what you mean by final explanation. But let's say if you're thinking of teleological explanations, I think they would still appeal to, let's say, things that will happen, so to speak. So in a way, you could say that even the explanation that we are talking about now, in terms of about the specific example that you brought up. So the explanation that I described there doesn't really appeal to anything that will or will not happen to this boat in question. It's just appealing to something that is possible. So in that sense, it's not appealing to some kind of final aim or kind of final goal of the ship that we're talking about, but it's saying just this: I've got an object on this boat, on this ship, which is a lifeboat, and I'd like to explain why it is there. So what's the how and why the kind of lifeboat is sitting there, and the statements about what has happened or happened in the past or will happen to the ship in question don't quite answer that question. Whereas if you refer to what is possible, what are the kind of set of possible configurations that the ship will have to go through, there is one where it might encounter like a sort of shipwreck. And that's the kind of thing that you have to refer to, this possibility for shipwreck. You have to use that in order to explain why the kind of lifeboat is there. I don't think this appeals to a final explanation, in the sense it doesn't appeal to some kind of overall aim of the kind of ship in question, or even just the final point of its trajectory, depending on how you define the final explanation. And I think that's the key. So somehow, the example I use is very parochial in a way, because it's talking about objects that are not really important for physics. But aside from that, I think the logic of a counterfactual explanation in physics is very similar. Because, for example, when you say, why is it that this particular quantum state is here for this quantum system? Of course, you can say, well, it's here because there was a state just before that, and then there was another state, and you can go back all the way from, since the start of the universe. That's one way of explaining that, which is the kind of law of motion type of way. But the counterfactual explanation is one that just says, well, the state is there because you were trying to perform a kind of measurement of position on a state which is an eigenstate of, say, velocity. And this is why actually you got this state here, because that can't be done to arbitrarily high accuracy. So I think you see, in this case, you're appealing to like this general principle of Heisenberg's uncertainty to explain why a particular state is there. And so that's the logic. That's kind of, out of the analogy, that's the same logic as in the lifeboat example.
Yeah. Because actually, I mean, it makes, it's more clear now, because you sort of have underlined the fact that it's a possibility, like it's a probability that something might happen. And I don't know, there is probability theory that mathematics that is defined, is rational thinking, is not like a theological explanation of what might happen. So yeah, this is now it's much more clear. Yeah.
Okay.
Thank you very much. I think also the audience will appreciate it.
Thank you.
Then actually, I have this other question actually, because when you were giving the example of physical counterfactuals, 2 out of 3 were about energy, and also Heisenberg's uncertainty principle can actually be reformulated in energy and time. So, what is the connection between actually the concept of energy and counterfactuals? Because it seems like that they sort of go hand in hand, like these two ideas.
Yeah, I like this question very much. It's, well, on the one hand, I have to say there is maybe just a less fundamental reason why all the examples were kind of referring to energy, because I guess it's perhaps one of the broadly known concept out of physics that maybe a broad audience can relate to. But fundamentally, I think there is an inherently counterfactual nature in the concept of energy, because the way we can talk about energy is in terms of what we can't do with it. So it's ultimately, if you like, it's what conservation laws tell us, right? So it's the concept of energy is very hard to define without having noted first that it is conserved in some way. And the fact that it's conserved means that you can't perform some transformations on physical systems. And so I think it's let's say, noting that there was a quantity that had to be conserved was actually the key to realizing, even historically, I guess, that energy is an important quantity to consider. Before that, we were not using energy as a concept, and we were using other things like forces and so on. And so I think the link is in this fact that whenever I think we are considering a quantity to be of interest in physics, it's either because it's impossible to change it, or, let's say in the case of entropy, because it's possible to change it in one direction and not in the reverse. So I think these are the two kind of key examples of that kind of impossibilities that actually led to noticing physical quantities that we were not aware of before. And so I think that's the key link between energy and kind of counterfactuals. I wonder whether this can be the start of a more general pattern where more and more quantities of the kind that energy is will be discovered by looking into counterfactual properties of dynamical laws. And kind of, it's a nice question. I like it. It's an open question.
Yeah, I mean, besides energy and entropy, are there any other counterfactual properties you can think of that play a role in physics?
Yes, so one is information. So I'd say, I think thinking about information in terms of as a quantity perhaps is not quite right. What we refer to as information is really this, the fact that on a given system that we think can contain information, some transformations are allowed. So the fact that some transformations are allowed, how many of them, for example, and which particular transformations is what defines the concept of information in physics. As I said earlier, right? So when you have like a bit, the fact that you distinguishing a bit from something that can be used as a bit is all about checking whether some very basic interaction can take place on this system. The permutations of the states, 0 to 1 and 1 to 0, and the copy or transformations that can copy 0 into another system and 1 into another system. So when we say a system contains information, we are implicitly referring to the fact that this system must have this set of tools available in a way. So this set of possible interactions available to it. And this is a very physical statement. So somehow, some constrained system may not have these properties and therefore can't be used as information carriers. So I think that's another important example of a quantity that kind of counterfaction is key to all sorts of fields.
I see. Then actually, considering since we have talked about information, since in your book you spend a lot of time talking about information theory, also counterfactuals probably can be expressed in the language information theory, I think. Not sure, but it seems like that.
Yes.
Do you think that it should be included as a core course in a physics degree? Because in our case, for example, we just briefly mentioned it in our statistical mechanics course, but just very briefly. So what are your thoughts about this?
Yeah, I think I really like this question too, because so the answer is yes. There should be I think I wish I had learned information theory first, and quantum information theory specifically, and then other, for example, all of these various quantum models that one studies in say physics, advanced physics degrees, are much better understood once you figure out the information theory that underlies a qubit, because so the kind of thing about information theory as seen from a physics point of view is that it somehow abstracts away all the details of particular dynamical models. So you don't have to worry about which particular differential equation you're solving, what coefficients you're putting in, and why. And you're just focusing on preparation of states and measurement and understanding how these things work. And I think somehow paradoxically in physics degrees, these phenomena are not treated at all, or they're treated just as kind of external. When you think of a measurement, you're always thinking of an external agent doing something to your system without actually modeling that agent or entity physically. And the first step to understand quantum information and quantum theory properly, in my view, is that you can apply the dynamical laws that you're using for your quantum system also to the measure, which is then the step to understand why, there are not, quantum theory makes much more sense than we thought. And I think this is true for physics in general, not just quantum theory. So yes, by all means, information theory from a physics point of view is needed, and I'd love for this to be, available to students if they want to kind of study it early on in their degrees.
Yeah, I see. We should mention it to the physics department sooner or later, I guess.
Yeah.
Okay. And then, there's just a final question that I would really love to ask. It is about the fine-tuning problem. Is it actually a problem? Because I was thinking, I was imagining myself like a hardcore experimentalist that is that thinks I do my experiment, what I get is basically a physical law, and there is no reason to ask why it's like that. Because the experiment determines what are the laws of physics. So how would you reply to such a, observation regarding this problem? Because you put some emphasis on this problem in your book. So what do you think?
Yeah, I think that in a way, maybe the fine-tuning problem is not formulated in a satisfactory way yet. So in that sense, we maybe have to think harder about what the problem really is. But if you want a more pragmatic version of it, which I think troubles me, is that if you look at these parameters that appear in fundamental laws, first of all, they are, as you say, they're just fixed so that somehow the laws match what we can observe in the lab. And this is not, I think, a satisfactory explanation in the sense that, yes, it's good to have the possibility of fitting these parameters in such a way that they fit the data. But there must be something deeper than just that. Because otherwise you could, in a way, say, well, if we go down that road, then you could say, well, actually, maybe I don't even need dynamical laws. I can see patterns in data and then try to guess, let's say, that they will be replicated in future experiments. And of course, this is a kind of caricature of this line of argument. But I think it seems to me that one way or another, if you take just the data as your kind of starting point to conjecture something without adding anything else, you may end up in this kind of extreme mode of thinking that, of course, doesn't make sense in physics, and no one does it like that. Yeah. On the other hand, there is the other fact that these parameters appear in the laws as C numbers. So they are numbers that obey, let's say, classical physics in a way. And so if you buy the idea that quantum theory is a universal theory, there is a sense in which you might want to think that perhaps these numbers are just a coarse-grained version of perhaps an unknown field or other thing that we don't know about yet, which could be described fully quantum mechanically in the same way that we know, say, quantum fields work. It's just that we haven't managed to kind of set up this theory yet. And of course, this is more like a kind of expectation that comes from the idea that quantum theory can apply to everything. But it's an interesting thing because it maybe shows how, by digging into why is it that these parameters are the way they are, we may actually think of clever experiments that can test this type of hypothesis. And first, maybe theoretical models and then experiments. So in that sense, I think it's a very concrete problem for physics that whenever we have a dynamical law, some aspects of it are not really explained. They're just fixed in a kind of ad hoc manner. And the idea is there a better dynamical law that can explain those too? And I think that's a fruitful line of inquiry. It's kind of proven successful in the past, and I wouldn't be surprised if this happened again.
Oh, yeah, I understand. I mean, let's say that also, like from an historical perspective, physics has developed in this way. So I mean, theories that can explain the parameters in other theories. So
yes, it sounds like yeah. So I guess this problem is not only, I think, is important from a conceptual point of view, but I think it's a fruitful way to maybe look into ways of thinking of new experiments, different experiments, that we really desperately need new experiments in general. I think we are not thinking hard enough, in my opinion.
Yeah, I see. Then there is just a final point that I would like to clarify. That is, I don't know, something that probably popped up in the mind of many people that were listening to your talk, just at the very, very beginning. I mean, why a computer cannot be programmed to make a copy of itself? I mean, this is just like, I mean, if it's possible to explain it like in a reasonable amount of time, because I mean, it's just like something curious that I mean, someone might want to understand.
Yes, I think so. The best way to read about this is this lecture that von Neumann gave at I think it was a symposium with biologists as well. So it was quite nice. And so first thing that I have to say is that what I said is not that the computer, universal computer, can be programmed to simulate self-reproduction, because of course, you can program it, and in the workspace there'll be a cluster of bits qubits, depending on the kind of computer you have, which will correspond to a cell, and then there's another cluster that corresponds to the raw materials, and then you can wait a bit, and then there's going to be a copy of these clusters. So in that sense, I think you can simulate, all right, the self-reproduction. It's obviously an allowed physical process, and by universality of computation, you can do that. So within the scheme of Turing machines, this is allowed. What is not allowed is so the computer doesn't have, other than its workspace, it's just, if you look into the way Turing defined the kind of classical Turing machine, which then kind of informs also the quantum Turing machine, it only has a workspace, it has a way of writing over it, zeros and ones and so on. And it doesn't have many other tools to work with. So there is no way for a computer to just get raw materials as input, physical bits of stuff, and assemble them together into a copy of itself. It's just not designed for that. There are no implements for it to kind of perform that. To do that, you have to add stuff. And von Neumann listed, even just in the logical architecture of a computer, you have to add things for this process of self-replication to be possible. And so von Neumann kind of listed the minimal amount of components that you have to add in order to be able to perform this task of self-reproducing. And there's an interesting problem, both for physicists and computer scientists, and maybe also biologists, where you're thinking, what is the smallest machine with the property that it can be programmed to create a copy of itself? And this is kind of an interesting problem. But I think you can't get a Turing machine to do that. And this is simply because the architecture doesn't allow for that. It's not part of the Turing model of computation. It's too simple in a sense.
Yeah, okay. So it has to do with the fact that, I mean, the Turing machine is made to give a printed output, not...
yes.
I mean, it doesn't have arms, or I don't know, robotic arms to assemble stuff.
Yeah. Yes, exactly. And so it's not, even the allowed input states, the allowed input substrates are just designed, there is only this state that can be fed to the Turing machine and nothing else. Whereas for constructing a replica of itself, you would have to fill to give the machine lots of other raw materials that are not quite a tape.
Yeah, it's clear. Carlos, do you have any further questions for Chiara?
I am afraid not. I think we are running out of time now, and perhaps we should finish now. So I would like to thank you, Chiara, for your time and really for the effort that you have made into exposing the foundations of constructor theory in such an accessible way. There are several comments in our feed saying how many people without perhaps a scientific background could understand this really well. It was really a pleasure to have
Thank you
you
very
at
much.
Oxford University Scientific Society. I would also like to thank everyone who joined us today, and I would like to say if you're interested in Chiara's research, I will encourage you to check out her book, The Physics of Can and Can't. Finally, I would also like to remind you that next week's lecture will also be online, and it will happen on Tuesday at 6:30 p.m. We'll be hosting Professor Richard Susskind, and he will be talking about the intersection of internet technology, artificial intelligence, and the legal system. I hope to see you there. Goodbye, and until next week.
Thank you very much. Bye.
Yeah. Bye.
Bye.